All right, a quick review. If we know an angle and then a side and then another angle, we call that angle, side, angle. If we know a side and then an angle, and then the next thing we know is another angle, that's side, angle, angle. If we know a side and then another side and then an angle, it doesn't have to be those two sides and that angle, but any two sides next to each other and then the next thing you know is an angle, that's side, side, angle. Side, angle, side is where you have a side and then an angle and then a side. So the angle is between the two sides. Side, side, side obviously would be if you knew all three sides, and angle, angle, angle is if you know all three angles. As we've discussed on a previous video, we're not going to be talking about the angle, angle, angle case because it doesn't produce a unique triangle. There's no one triangle that we can get if we know all three angles of a triangle. There is actually an infinite number of triangles that will meet that particular set of criteria. But of the other 5 possibilities, we can solve a triangle, even if it's not a right triangle, if we know those 3 pieces of information. These 3 cases, we need the law of sines to solve a triangle. For these 2 cases, we need the law of cosines, and that's what this video is about. To talk about where the law of cosines comes from, I want to remind you that when we put a triangle in the coordinate system, we label the sides x, y, and r. And this point has coordinates r cosine theta for this angle theta, comma r sine theta. With that under our belt as a reminder, I'm going to move this out of the way. I'm going to draw another triangle. This triangle is set at the origin. I have to get all my pieces in a row here. It's got a vertex at the origin, and it has this angle is labeled A, this angle is labeled B, and this angle is labeled C. The coordinates of angle A are 0, 0. The coordinates of angle B are C0 because this is length C. This is side C because it's opposite angle C. The coordinates of this point right here are r cosine theta, r sine theta, but our r and our theta are different in this diagram than they were on the previous one. Our r is this length right here, and that's the side opposite angle B. So we'll call that side B, and we'll relabel these B cosine theta and B sine theta. And the angle that we're looking at here is angle A. So we'll just rename our angles while we're at it. Cosine theta becomes cosine A, sine theta becomes sine A. So now we have the coordinates of this point right here. I'll also label this side little a and this side down here little c. And while I'm at it, I'll label the height of the triangle h. Now I'm going to take a look at the x and y coordinates of the point where the angle C is at the top of the triangle, this vertex of the triangle right here. I can call it b cosine A, comma b sine A, but I want to look at another way to think about the x and y coordinates as heights along the y-axis, as a height along the y-axis, and as a distance along the x-axis. Okay, maybe not a different way to write them, but I'll be using them in a different way. This is the y-coordinate b times the sine of a, and this is the x-coordinate b times the cosine of a. The reason I'm doing this is that I want to find a way to represent this triangle right here, because this is a right triangle. I could do it with the other triangle as well, but I'm going to do it with this one. The other thing I'm going to do temporarily is give this, the base of the right triangle I'm playing with here, a label. I'm just going to call it T. It's just temporary. I want to do that because I want to make the point that because this is a right triangle, I can write T squared plus H squared equals A squared. Now, T I can think of as the x-coordinate C. This is a length, right? So the x-coordinate C minus the x-coordinate B times the cosine of A. So let's rewrite T as c minus b cosine a. Of course, it's all squared because it's t squared in this equation. H is just b times the sine of a. It's also a distance, but it's the distance from here back down to the x-axis. So that's b times the sine of a minus 0. That is all equal to a squared, little a squared. Now let's do some algebra. I get little c squared minus 2 times bc cosine a plus b squared cosine squared of a plus b squared sine squared of a equals a squared. All right, now I'm going to rewrite this part. C squared minus 2 times b times c times the cosine of a plus, I'm going to factor that b squared out. I get cosine squared of a plus sine squared of a. That's all still equal to little a squared. Making the observation that sine squared plus cosine squared equals 1, I can rewrite this again as c squared minus 2bc cosine a plus b squared equals a squared. And if I rewrite it one more time, just kind of tidying things up and changing the order that some of the variables are in, I get a squared equals b squared plus c squared minus 2bc times the cosine of a. And that is called the law of cosines. Now, I did this a little bit differently than the way it was done in your book. In your textbook, they give you the formula and then they prove it. They do it, though, by using a triangle with an obtuse angle in it, something larger than 90 degrees. And I wanted to show you that the law of cosines holds even if the triangle only has acute angles in it. So between the version in your textbook and the version you have here, you now know that the law of cosines holds regardless of the size of the triangle. It's also worth pointing out that if I relabeled my angles, say A, B, and C, then I'd have to relabel my sides as well. This would be my A. What did I say this was? B? That would be B, and this would be C. But if I did that, the coordinates would change, the height would be based on a different difference. All that to say, I would come up with a different version of the law of cosines, but it would be equivalent. I'm going to erase this reminder and replace it with all three versions of the law of cosines. In a face-to-face class, I let my students use an index card, but only a 3x5 index card to put notes on. With trigonometry especially, that's not a lot of space, and as the course goes on, you start to run out of room in your note card before an exam. So one thing you can do is just put one version of this formula on your note card, say this one here, and remember the pattern. What I mean by the pattern is that you'll notice that if the thing starts with an a squared, a side a squared, then it's the cosine of angle A that you have to use in your formula. If you have a b squared at the beginning, then it's cosine of b. And if you have a c squared, it's the cosine of c. Once you've decided which version you're going to use, the A version, the B version, or the C version, you'll notice that if you use the A version, everything else in the formula is the other two sides, B and C. So if I have A here and here, I have B and C here and here. If I have B at the beginning and end, I have A and C, the other two sides, in the other two positions. And with the C version, I have A and B in those positions. There's actually another version of this formula, and some of you may know it, some of you may use it, some of you may find it in the process of Googling and watching other YouTube videos, but I'll just show you where it comes from. And then again, remember that you don't have to memorize another formula. You can always derive that one from this one. Let's just do it together. If I take a squared equals b squared plus c squared minus 2bc times the cosine of a, but what I want is not this unknown side. Say I have sides b and c, and I have the angle of a, and I'm looking for a squared. That's when I would use this version. But what if I have all three sides, and I'm looking for the cosine of angle a? I'm still going to use this version of the formula to start with. But since I'm looking for a, I want to solve it for cosine a. So I'm going to subtract b squared and c squared from both sides. That leaves me with negative 2bc cosine A on the right-hand side. And then I'll divide both sides by negative 2bc, which leaves me with just the cosine of A. So I get the cosine of A is equal to a squared minus b squared minus c squared all over negative 2bc, which, if you prefer, you can write as b squared plus c squared minus a squared all over positive 2bc, your choice. Now, I've just found this so-called formula very easily by doing some algebra on the original version of the formula. And then I can either rederive this formula whenever I need it, or I can just plug the values in that I do have. If I only have sides and I don't have the angle, I could plug the sides A, B, and C in here. These will all be numbers, and then turn around and solve that equation for the cosine of A. Of course, using this version of the formula, the cosine of A equals some number. And to find out what that angle A is, you'll have to take the inverse cosine of that number. Okay, let's take a look at a couple of examples. Let's take a look at the side angle side case first. I've written the formula up here, so we have it to refer to, and I've got a triangle that's labeled with a side, another side, and the angle between them. That's two sides and the angle between them. The notation matches the situation. All right, the law of cosines tells us that a squared equals b squared plus c squared minus 2 times b times c times the cosine of A. Well, I know what A is. It's 37. Do I know what B and C are? I do. They're 10 and 15. So side A squared is going to be equal to side B squared plus side C squared minus 2 times side A times side B times the cosine of A. And A is 37 degrees. The rest is calculator work. I mean, I can do some of this as mental math, but you don't really have to. Let's see, that's going to be 20 times 30. This will be 300. I'm going to have to do this cosine of 37 on a calculator anyway. 100 plus 225 is 325 minus 300 cosine of 37. I will say this, it's very tempting to subtract these numbers here, but don't do it because the order of operations tells us we have to do this multiplication first. It turns out that the cosine of 37 degrees is about 0.7986. I'm just going to go with 0.799 for now. And when I do that multiplication, multiply that by 300, I get 325 minus about 239.590. I'll just call it 0.6. Remember, this is just record keeping. I'm keeping a much more accurate record of the decimal that my calculator knows about in my calculator, so I can use it. So for my final computation, well, almost my final computation, I'm going to take 325 and subtract second answer. That gives me 85.409. I'll call it 0.41. And then for the last computation, I'm going to take the square root of both sides. I end up with A is approximately equal to 9.241717751. I'll go with 2417. And that tells me the length of this side, 9.2. So now I have all three sides. More importantly, I have a side and an angle opposite each other, where both of those are known values. I don't have that in either of the other two cases. I don't have side B and angle B or side C and angle C. In fact, I have side C and side B, but neither of the other angles. I could use the law of sines now, though, because I have opposites. I know these opposite values. I could use the law of sines to figure out angle C or angle B, and then just the angles of a triangle add up to 180 trick to find the third angle. So the law of cosines is really quite handy in this particular case. Let's take a look at an example. What if you wanted to find the distance between the two mountaintops here? We'll draw a sketch to represent where you might be standing, looking at the two mountaintops. You can use an instrument called a theodolite. It's a surveyor's instrument to find the angle between the two mountaintops. Essentially, you set the theodolite at 0, and then you rotate it and you measure the angle it's facing, and it tells you the angle between the two objects you're looking at. We'll assume that's 51 degrees here. You'll also need to know how far it is to each of the mountains. Let's say this one's 31 miles, and this one's farther away, so that's 52 miles. How far is it between the two mountaintops? Well, now we have a side angle side situation, so we'll need to use the law of cosines. Another way to tell that it's the law of cosines and not the law of sines is that in no case do I have two opposites that are known. This angle has an unknown side opposite it. Both of these sides have unknown angles across from them. So it's definitely not a law of sines problem. The law of cosines says that a squared is equal to b squared plus c squared minus 2bc times the cosine of a, where a, side A, and angle A, sides B and C, are yet to be determined. Since I know I'm looking for the distance between the two mountaintops, I'm going to go ahead and let that be my A. And that way I can very easily plug in B and C and angle A and get my answer. So I have a squared is equal to 31 squared plus 52 squared minus 2 times 31 times 52 times the cosine of 51 degrees. And the rest is calculator work. My calculator tells me that a squared, when I do all the arithmetic on the right-hand side there, is 1,636.0711, or thereabouts. Let me change this to an approximation. If I take the square root of both sides, I get A is approximately equal to 40.44837, so 4484. That's a lot of fours. So this is my answer. It's the distance between these two mountaintops. All of my linear distances are measured in miles, so my unit here is also miles. And that's my answer. Not too bad. What happens if you have all three sides? Let's take a look at that on a different screen. Okay, here's a triangle for which we know the lengths of all three sides. Let's write the formula out again. A squared equals b squared plus c squared minus 2 times b times c times the cosine of A, and that's angle A. Now, if I'm going to plug my values A, B, and C into this formula, I need to know which ones they are. It doesn't actually matter, but it's a good idea to label them so that you're using the same values for A, B, or C in every place in your formula where you see that variable. So now what I have is 6 squared equals 8 squared plus 11 squared minus 2 times 8 times 11 times the cosine of A. Now, because I have all the sides and not the angle, this is the piece that's missing, and I need to solve first for the cosine of A, and then eventually, by taking the inverse cosine, solving for A. This is where that other version of the formula that I showed you comes in handy if you prefer. You can write this formula, you can rewrite this formula in terms of, for cosine in terms of all the other variables if you want to before you begin. I like just using this. I mean, that way I only have to have one formula memorized, and then I can always solve for the cosine of A at the end. It's up to you, of course. Everybody's got their own personal preference. I'm just going to do it this way, though. Let's see, I have 2 times 8 times 11, so that's 16 times 11. I think I better just do that on my calculator. That's 176 times the cosine of A. Now I can add these two values together, but I can't subtract this one because it's part of a product. So remember your order of operations here. 121 and 64 is 185. I can subtract 185 from both sides, though. That's going to give me negative 149 equals negative 176 times the cosine of A. And then I can divide both sides by the negative 176. Those are gone, leaving me just with the cosine of A. And 149 over 176 is 0.8466, approximately. To find the angle A, I need to take the cosine inverse of the cosine of A. So I'll do that to both sides. This leaves me with just A, and then when I take the cosine inverse of what I have on the screen on my calculator, I get 32.1572 degrees. This is an angle, so my units are degrees. So now I know the size of this angle right here. It's about 32 degrees. I'll write that down kind of as a record-keeping policy, but the actual value I would give in an answer would be this one here, or maybe even a more accurate one. It just sort of depends on the context. I've written it down here just as 32 degrees to help me remember that's the one I just found. This is just for my own benefit, really. I can now go on to do either the law of cosines again and find a different angle by starting with a different variable here. If I start with c squared, then I'd end up looking for cosine of c in my formula here. C squared here gives me cosine of c here, and I'd have a and b here and here. And the same thing for b squared. I can do that. In fact, let's go ahead and do one of them that way at least. Let's find the angle b by using the formula b squared equals a squared plus c squared minus 2ac times the cosine of b. These two letters match. One's the side and one's the angle, but the beginning and the end match, and in the formula, the other two variables come into play. So this time around, I have b squared, which is 8 squared, equals 6 squared plus 11 squared minus 2 times 6 times 11 times the cosine of b. That's 64 equals 36 plus 121 minus 11 times 12 is 132 times the cosine of b. I'll just do the rest of the arithmetic off screen. So if the cosine of b is about 0.7, then b is about 45.2 degrees. And there you have it. Now let's put that in place as a record-keeping device. B, angle B, is about 45 degrees. And now I can find angle C just by subtracting these two from 180. I get 102.6356. Now, that is an approximation. Let's do this one in blue. That's an approximation, but it's a fairly accurate approximation because to find this angle, to find the measure of angle C, I took 180 degrees and I subtracted from it not 45.2072, but the value that was in my calculator. and not just 32.1572, but the value that was in my calculator, which is accurate to a great number more decimal places. So I know this is accurate as well. If I add all three of these up, I may get a value just under 180 degrees. It might be 179.997 or something. But that's because even these are approximations, as accurate as they are. So you always want to use the most accurate values you can. And oftentimes that means referring back to the values that you found in your calculator. You can either scroll back up to them if you have a calculator that will do that, or recalculate them if you need to. You could write them down to a great number of decimal places, but that's a bit of a pain. Or you could stick them in your calculator's memory. That, of course, requires that you learn how to use your calculator's memory. It's not as difficult as it used to be. The olden days, the calculator memories were really, really awkward. Anyway, my point is, be as accurate as you can, but that's how you use the law of cosines. And specifically, that's how you use the law of cosines. If you have all three sides of a triangle and none of the angles, you can still find the angles if you have all three sides. So now we've covered all 5 instances of a case when you have 3 pieces of information of a triangle and you want to find any one or all of the other 3 pieces. The only one that we can't do this with is the angle, angle, angle case, the case where you know all 3 of the angles but none of the sides. That doesn't produce a unique triangle, so we can't really do anything in that case. But we've done now all 5 of the other cases, and we've done a couple of applications as well. So I hope that's enough for you for this topic, and we'll see you in the next one.